Hi everyone, welcome to CHM 202 Colloidal Surface Chemistry Lecture 8, where we'll be looking at processes that affect emulsion in liquid form stability. In particular, we'll look at creaming, sedimentation, which is peculiar to emulsions, flocculation, Ostwald ripening, Coalescence, phase inversion, which is also peculiar to emulsions. Then we'll look at processes that affect the stability of colloidal suspensions. In particular, we'll look at sedimentation and flocculation. Then we'll look at ways of kinetically stabilizing emulsions in liquid forms. In this case, we'll look at charge stabilization, steric stabilization, and Pickering stabilization. Then we'll move to ways of stabilizing colloidal suspensions. In particular, we'll look at particle size reduction, increasing viscosity of the continuous liquid phase, matching the particle density with the density of the liquid. We'll look at charge stabilization and then steric stabilization. After the lecture, I expect you to be able to name and discuss processes that affect emulsion in liquid form stability. I expect you to be able to name and discuss processes that affect the stability of colloidal suspensions. I expect you to be able to name and discuss the various ways through which emulsions in liquid forms can be made kinetically stable. I also expect you to be able to name and discuss the various ways through which colloidal suspensions can also be made kinetically stable. But before that, what are we referring to as stability? Let's take a classical case of oil and water. Oil and water are immiscible. Add oil to water, oil floats on top of water because water is more dense than oil. Then you share this mixture vigorously in the presence of some form of substance called an emulsifier that blends the oil and water so that you now have either oil droplets in water or water droplets in oil. This is what is called an emulsion. An emulsion is basically a homogeneous mixture of, macroscopically, mixture of two immiscible liquids, in which one of the liquid is dispersed as microscopic droplets in the bulk of the other one. This is what we have. This is a stable emulsion, one phase. This is what we expect. It's our holy grail in colored science. And this is an unstable emulsion with an emulsion layer and a separated liquid, one of the liquids making up the emulsion. So this is what we're referring to as stable system. So in colored science, when we talk about stability, we're referring to systems, be it emulsions, foams, colloidal suspensions. We expect systems to be a single phase, not to be separating out. Systems that separate out, we consider them to be unstable. And those that remain one phase, in quote, macroscopically, we call them stable systems. And that's what we always aim for. There are certain processes that are responsible for destroying the stability of colloidal systems, and that's what we'll be looking at in terms of emulsions, foams, and colloidal suspensions. So processes that affect the stability of emulsion include creaming, sedimentation, flocculation, Ostwald ripening, phase inversion, and coalescence. Creaming typically occurs in oil and water emulsions. Creaming refers to the upward movement of oil droplets, either under gravity or in a centrifuge, to form a concentrated layer at the top of the emulsion without any change in the droplet size distribution. On the other hand, sedimentation occurs in water and oil emulsions. and it refers to the downward movement of oil droplets under gravitational or centrifugal force field. I've made here an animation of what happens in sedimentation as well as what happens in creaming. So in sedimentation, if you consider these grain circles as emulsions, droplet, sedimentation, the droplets move downwards, creaming, the droplets move upwards. And for both sedimentation and creaming, there is a concentrated layer, either down for sedimentation or upwards for creaming. Creaming and sedimentation are a consequence of the difference in density between the dispersed and the continuous phases of the emulsions. In creaming, the droplets are less dense than the continuous liquid phase, whereas in sedimentation, the droplets are more dense than the continuous liquid phase. I've shown here photographs of creamed and sedimented emulsions. This is a creamed emulsion, oil and water emulsion. This is the emulsion layer with oil droplets, and this is a resolved layer of water. Here, resolved oil layer, and we have here emulsion layer with water droplets. For the case of a very dilute emulsion, that's emulsion with the fraction of the dispersed phase droplet less than 0.02, the creaming speed or sedimentation speed can be expressed by a mathematical expression, bearing in mind that the droplet has a density of rho, radius r sub d, and is moving in a continuous liquid phase of density rho sub L and viscosity eta. We can write the creaming or sedimentation speed as in equation 1. Based on this equation, m is the mass of emulsion droplet, J is the acceleration due to gravity, and change in eta represents the difference in density between the emulsion droplet and the continuous liquid phase. Based on equation 1, which I have sort of written it there for reference, creaming or sedimentation speed decreases with decrease in emulsion droplet size, decreases with decrease in density difference between the emulsion droplet and continuous liquid phase. This is the density difference there, and this is the radius of the particle which characterizes the size of the droplet. The creaming or sedimentation speed also decreases with increasing viscosity of the continuous liquid phase. That is, creaming or sedimentation speed is inversely proportional to the viscosity. Therefore, in dilute emulsions, creaming or sedimentation can be suppressed by reducing the average droplet size, reducing the density difference between the emulsion droplet and the continuous liquid phase, as well as or increasing the viscosity of the continuous liquid phase. Flocculation refers to the aggregation or clustering of emulsion droplets without the rupture of the stabilizing thin film. The thin film is the coating between the emulsifier and the droplets, inner droplets of the emulsion. So I've shown here the optical micrographs of a flocculated and a non-flocculated emulsion. This is what happens. This is a flocculated emulsion with the droplets aggregating or sticking together without actually merging. And this is an example of a non-flocculated emulsion where the droplets are actually simply touching but they are not stacked on each other like what we have here in the flocculated emulsion. Flocculation is enhanced by the polydispersity of the emulsion, that is, the non-uniform size distribution of the emulsion. In the case of surfactant-stabilized emulsions, surfactant-stabilized emulsions are emulsions stabilized by surfactants. Flocculation usually occurs because the interaction energy, which is denoted as U of D, between the two droplets are slightly negative within that separation. And here is a sketch of the plot of the interaction energy against the distance of separation. What we've got here is this primary minimum, here is the primary maximum, and this is the secondary minimum. So basically, for this case, the droplets are in the secondary minimum. Flocculation in particle-stabilized emulsions, that is, emulsions that are stabilized by small solid particles, basically results because the particle layer is being shared by the emulsion droplets. So this is known as particle bridging. And unlike creaming and sedimentation, which are reversible, flocculation may be either reversible or irreversible. In surfactant-stabilized emulsions, for instance, whether or not flocculation will be reversible depends mainly on the strength of the interdroplet forces. When they are weak, then flocculation is reversible. When they are strong, flocculation is irreversible. Flocculation resulting from particle bridging in particle-stabilized emulsions are basically, in that case, irreversible. Here is a sketch of a particle layer being shared by or bridging two emulsion droplets. That's one particle layer started that way, and that point there, the two emulsion droplets share that layer. This is another case by way of comparison. These are two particle layers on the different emulsion droplets. They are unbridged. So this behavior of the particle causes flocculation, and because these particles are rigidly held this position, it's difficult to cause irreversible flocculation. Flocculation enhances creaming and sedimentation. That's the sad news, because dilute emulsions, flocculation enhances creaming and sedimentation in dilute emulsions, so to say. And this is because flocks rise faster than individual droplets due to their large effective radius. For the case of concentrated emulsions, what happens is the formation of a gel-like network strengthens the emulsion stability. Therefore, flocculation does not enhance creaming or sedimentation. Ostwald ripening refers to isothermal distillation or molecular diffusion, by other terms, actually refers to the growth of large droplets at the expense of smaller ones. In Ostwald ripening, what basically happens is there is a diffusion-driven mass transport of the dispersed phase molecules from one emulsion droplet, basically the smaller one, through the continuous liquid phase to the bigger one, due to the difference in the solubility of the molecules in the bigger droplet and those in the smaller droplet. Solubility actually of spherical substances increases with decreasing size in accordance with the Kelvin equation, which is given by equation 2. Based on equation 2, C of x refers to the solubility of molecules of the dispersed phase from the spherical droplet, C of infinity refers to the solubility of molecules of the dispersed phase from a planar interface, that is a flat interface. For this case, it's a spherical droplet or spherical interface. Gamma represents the interfacial tension between the liquid phases of the emulsion. V sub m refers to the molar volume of molecules of the dispersed phase liquid. X refers to the radius of the dispersed droplets. R refers to gas constant, and T the temperature. Coalescence, on the other hand, refers to an irreversible process whereby two or more emulsion droplets fuse together to form one single droplet. In this case, the interaction energy between the droplets is significantly negative, that is, lies in the primary minimum within that given separation of the droplets. So this is another a sketch again of interaction energy against the distance of separation. This is the primary minimum where the particles now reside in coalescence, and as usual that's the primary maximum, and this is the secondary minimum. I've shown here an optical micrograph of the various stages of a coalescing water and oil emulsion. These are water droplets in an oil emulsion. The oil is basically heptane. Within the first few 10 seconds, the emulsions are intact. As the heptane phase begins to evaporate, the droplets begin to deform like deflected footballs. By 78 seconds, majority of the droplets have been deflected. At 120 seconds, the droplets now begin to merge gradually. By 149 seconds, there is significant merging. By 163 seconds, there is clearly merging of the droplets. We published these findings. This was one of the work I did, and we published the findings in this year, 2021, in Journal of Colloids and Surfaces. I've shown here a movie of coalescence in a multiple emulsion. Of course, multiple emulsions contain emulsion globules, and in those globules there are emulsion droplets. So this is what we've got basically, and if we play this movie, if I play this movie now, you will see that these droplets, two droplets, and that one have merged together into a large big droplet. Phase inversion refers to the changing of one emulsion type, say oil and water, to another type, say water and oil. And it is favored by a change in the composition or environmental conditions of the emulsion, like for instance, emulsion dispersed volume fraction, emulsifier type, emulsifier concentration, solvent conditions, temperature or mechanical agitation. There are two types of phase inversion: transitional and catastrophic phase inversion. In transitional phase inversion, there is a gradual change in the emulsion phase towards another one, and this is induced by the change in emulsifier type, change in emulsifier concentration, solvent conditions, emulsion temperature or mechanical agitation. On the other hand, catastrophic phase inversion is a sudden change of one emulsion type to another one, and is driven mainly by a change in the volume fraction of the component liquid phases. What scientists believe is that the physicochemical basis of phase inversion is extremely complex and involves aspects of flocculation, coalescence, and emulsion formation. Here is the relationship between the processes that affect emulsion stability. Here is a kinetically stable emulsion which can undergo phase inversion to another emulsion. Bear in mind the green dots represent, green circles represent one phase, while the white background represents another phase. So when there is a phase inversion, the green one now becomes the continuous phase, while the white phase in coal becomes the dispersed phase. This emulsion can undergo flocculation. This is flocculation. In flocculation, it enhances coalescence. And once coalescence occurs, that will lead to phase separation. This emulsion can also undergo either creaming or sedimentation depending on the difference in density between the liquid phases. Creaming also enhances coalescence, and coalescence can lead to phase separation. Flocculation enhances sedimentation or creaming, and once that happens, that can also lead to coalescence and phase inversion. The emulsion can straight away undergo Ostwald ripening, and Ostwald ripening also leads to phase separation. Processes that affect liquid form stability. The processes that affect liquid form stability include drainage or creaming, also ripening and coalescence. Drainage or creaming refers to the physical separation of the gas bubbles from the continuous liquid phase due to the effect of gravity. When foams drain, light gas bubbles move upwards, forming a denser foam layer at the top, while the heavier liquid phase remains at the bottom. Here is a photograph of a creamed aqueous foam. This is the foam layer, this is the aqueous layer. And actually the gas bubbles have moved upwards. That's why I've drawn this arrow pointing upwards. After creaming, the gas bubbles accumulate at the top and they rearrange and they deform into highly packed forms with polyhedral cells. These are polyhedral cells. Of course, I should mention to you, this is an optical microscope of this. The polyhedral cells, especially if the forms are stabilized by a surfactant. And this forms a three-dimensional microstructure that is characterized by a thin film or lamella. And this is the thin film. Well, here is thin film, and as well as plateau borders. And that's a plateau border. That's another one. That's another one. Where there is the intersection of the three thin films. That's one thin film. That's another one. And that's another one. Coalescence actually refers to the case whereby two gas or more gas bubbles merge together to form a stable form a big gas bubble. And coalescence occurs because the thin films formed after drainage are not stable enough to keep the touching cells apart, and that results in the neighboring bubbles merging together. Ostwald ripening, or disproportionation, if you like, is the case whereby large gas bubbles grow at the expense of smaller ones, just like what we had in emulsions. And this is driven by the difference in the Laplace pressure between the bubbles because they're of different sizes. Bear in mind, if you look at the equation for Laplace pressure is inversely proportional to the radius. This is a radius of a gas bubble, so to say. This is gamma, the surface tension of the liquid in which the gas bubble is in. If you can see, the smaller the gas bubble, the higher the Laplace pressure. And the bigger the gas bubble, the less the Laplace pressure. So these pressure differences actually are responsible for Ostwald ripening in foams. Because of the difference, the difference in the pressure, there is diffusion of gas molecules from the smaller gas bubbles through the continuous liquid phase to the larger ones over time. And here is the relationship between the processes that affect the stability of liquid foams. This is a kinetically stable foam. It can undergo foam drainage. Foam drainage enhances coalescence, and coalescence leads to phase separation. This can also undergo Ostwald ripening, and that can lead to phase separation as well. The processes that affect the stability of colloidal suspensions include sedimentation and flocculation. Flocculation is also called coagulation. Sedimentation is the settling down of particles under gravitational or centrifugal force field. And what happens is bigger particles settle down faster than smaller ones. And if we look at the case of dilute suspensions, suspensions in which the fraction of particles is less than or equal to 0.1. If we take U to be the settling speed, and if we consider an isolated spherical particle of radius r, so p, and the density of the particle is rho, so p, in liquid of density rho sub L, and the viscosity of the liquid is eta, then we can write an expression that represents the increment speed, the sedimentation speed, so to say. And based on this equation, m is the mass of the particle, g is acceleration due to gravity. A change in rho represents the density difference between the particle and the continuous liquid phase. Ways of stabilizing emulsions and liquid foams, that is, ways of preventing foams and liquid foams and emulsions from separating into their component component phases. Can do that by using charge, steric, or Pickering stabilization. Charge stabilization is due to the presence of charges on the surfaces of this dispersed phase, droplets, or gas bubbles. And the charge can be brought in by the presence of anionic surfactants on the surfaces of the droplets or gas bubbles, or for particles, if they are charged, that can lead to the presence of charges on the surfaces of the dispersed phase droplets or gas bubbles. Because of the presence of the charges, there is an electrostatic repulsion when the droplets or the gas bubbles come together because of the overlap of the electric double layers on them repel each other. I've made a cartoon here of a case where there is repulsion between oil droplets in emulsion and foam bubbles in foams. What we know in nature is that like charges repel while unlike charges attract. So because we have like charges on both sides, there will be repulsion. Charge stabilization is responsible for the stabilization of aqueous emulsions or liquid foams. In the case of stabilization using ionic surfactants, which could be anionic or cationic. Charged stabilized emulsions and liquid foams are prone to destabilization when electrolytes are added. because the presence of the electrolyte screens the charges on the dispersed phase droplets or foam bubbles, and that leads to van der Waals forces becoming stronger, and that can cause destabilization when they merge together. Added electrolyte, on the other hand, added electrolyte, so to say, I've said that before, charge stabilized emulsions and foams are also destabilized by charge neutralization, usually by adding oppositely charged surfactant, ionic surfactant in this case. Steric stabilization. Steric stabilization results from the attachment of long-chain polymer molecules to the dispersed phase droplets or gas bubbles in the case of foams. When this happens, there is limited interpenetration due to the presence of the polymer chains, and that causes steric hindrance. The limited interpenetration of the polymer chains on the dispersed phase surfaces leads to an effective repulsion due to osmotic effect or elastic effect. Unlike the case of charge-stabilized emulsions and liquid foams, which are prone to added electrolytes, steric stabilized emulsions and foams are insensitive to added electrolytes. That is, addition of electrolytes don't cause them to become unstable. Again, unlike charge-stabilized systems, which work only in aqueous systems, steric stabilization is effective both in aqueous and non-aqueous systems. Pickering stabilization. This is stabilization due to the absorption of small solid particles on the dispersed phase surfaces. In some cases, it is possible to add surfactants to the particles. And when surfactants are used in combination with particles, the aim is usually for the surfactants to absorb on the particles and alter their workability and improve the extent to which the particles can stabilize either the emulsion or the foam system. Emulsions or liquid foams stabilized in this manner are known as Pickering emulsions or foams. This is after the name of one of the scientists that started investigating the use of small solid particles in emulsion and foam stabilization. Once the particles are on the surfaces of the dispersed phase, the droplets of gas bubbles, the particles prevent the droplets or gas bubbles from merging together by acting as a mechanical barrier. I'll show you what that means. This is an emulsion droplet or gas bubble coated with small solid particles. This green bit represents either a gas bubble or an emulsion droplet. And this is another one. When they come together, because of the presence of the particles hinder the inner droplets for emulsions or gas bubbles from merging. And that is what is referred to as a mechanical barrier. On this slide, I've shown a case where the emulsion is stabilized by calcium carbonate particles. And I should have mentioned to you that in particle stabilized emulsions, Pickering stabilization, in quote, both spherical and non-spherical particles can be used. Here is an example of a case where non-spherical particles have been used to stabilize oil and water emulsions. And the particles are rod-shaped calcium carbonate particles. I did this experiment during my PhD at the University of Hull under the watch of Professor Bernard Binks. So I prepared this emulsion, and after preparing them, they were frozen. A sample of it was frozen and allowed to evaporate. That is, the continuous water phase was allowed to evaporate at very low pressure. And I exposed the oil droplets, which are shown here in the image and have been illustrated here in the sketch. This is frozen, partially exposed oil droplet, and these are the rod-shaped calcium carbonate particles, and that's frozen water. If you look closely, you can find, or see rather, the rod-shaped particles on the surfaces of these exposed oil droplets. Pickering emulsions and foams are more kinetically stable than surfactant stabilized emulsions and foams, because the strength with which the particles are held on the dispersed phase droplets or gas bubble is far higher than the strength with which surfactant molecules are held. And this strength for particle is quantified in terms of particle detachment energy. And the particle detachment energy is basically the minimum amount of energy required to remove a particle from an interface into one of the bulk liquid phases. So for the case of a spherical particle at a planar liquid, say liquid 1, liquid 2, or liquid 1 air interface, the particle detachment energy, denoted as change in G superscript det. This is a particle, this is it, this interface and that interface, and this is the radius of the particle, r sub p, and this is the interfacial tension. The energy can be given by equation 4. This is the interfacial tension radius of the solid particle, and theta 1 to 3 represents 3 phase contact angle. That is phase 1, 2, 3, so to say. Equation 4 is valid only for an adsorbed particle that is initially in the less polar phase. And I should mention to you that once you have two phases, one phase is basically going to be less polar than the other one, at least to some level. So the positive sign in the brackets of equation 4 changes to negative if the particle if the particle was initially in the more polar phase. And that means sign in this, that's what I'm referring to, the sign in this bracket will change from positive to negative. If you recall, we had positive there, and we now have negative here. Ways of stabilizing colloidal suspensions. Basically, that can be achieved by reducing the particle size, increasing the viscosity of the continuous liquid phase, matching the liquid density with the particle density, and charge or steric stabilization, decreasing particle size or increasing the viscosity of the continuous liquid phase, or matching the liquid density, stems actually from this equation, the sedimentation speed equation. Based on this equation, the sedimentation speed is directly proportional to the square of the radius of the particle. That is, if you increase the radius of the particle, sedimentation is going to increase. If you reduce it, it's going to decrease. Also proportional to the difference in the density between the particle and the liquid continuous phase. And inversely proportional to the viscosity of the continuous liquid phase. So that when viscosity increases, there is decrease in sedimentation. When viscosity decreases, there is increase in sedimentation. Charge stabilization. The charge density of colloidal particles in aqueous suspension can be tuned by adjusting the pH of the continuous liquid phase. The presence of charges causes an electrostatic repulsion between the particles, and that prevents aggregation. And by extension, aggregation strengthens sedimentation, and because aggregation is prevented, sedimentation is also prevented. Charge-stabilized suspensions are sensitive to added electrolytes, just like charge-stabilized emulsions and foams. As a result, they coagulate at a certain critical concentration known as critical coagulation concentration. And this concentration is inversely proportional to the 6th power of the charge on the electrolyte ion. Steric stabilization. This refers to the attachment of long-chain polymer molecules to the surfaces of the particles. Just like what we had in the emulsion in foams, the limited interpenetration of the polymer chains on the particle surfaces lead to an effective repulsion due to osmotic and elastic effects. Again, unlike charge-stabilized suspensions, which are prone to added electrolytes, steric stabilized suspensions are insensitive to added electrolytes. That is, electrolytes addition does not cause them to become unstable or rather lead to aggregation. Thanks for watching. I've left a link to the PDF version of this video in the video description.